Welcome back, folks. Now with glycolysis done, we're almost ready to jump into the citric acid cycle, or the Krebs cycle, depending on what textbook you read about it in. In order to do this, let's go ahead and take a quick recap of where we landed at the end of our first two videos. So the process of glycolysis generally was aimed at breaking this sugar into 3-carbon chunks that we could process a little more easily. We did that by adding phosphates to either side to sort of spring-load the molecule, and it broke into those two chunks. That required us to first invest a couple of ATP, but we eventually got back 4 ATP on the 2 that we put in, so a net gain of 2. And I actually have to correct this on the worksheet. It should be 2 NADHs. I only see 1 in one of the reactions, but it's a reaction that happened twice because it happened for each half of the original glucose. So far, we've got a net release of about 15 kilocalories per mole. That's a pittance compared to what we can get by burning sugar in air. So we want to do a little better. We could get a bit more out if we ferment the product, turning pyruvate into lactic acid, but that's still not terribly impressive. Most of the good stuff is going to require us to turn this all the way into carbon dioxide, and essentially that will be the goal of the citric acid cycle. As we take a look here at the beginning of this page, what we're going to be doing is trying to turn all 3 carbons in that pyruvate to carbon dioxide and generate some ATP in the process and reduce a whole bunch of coenzymes. Now, to do this, we're going to do a lot of oxidation. We're also going to need decarboxylation, which is a reaction we haven't talked a whole lot about so far. So let's take a moment just to discuss what that's going to look like. In particular, there's a form of it called oxidative decarboxylation that we're going to do very early on here and one more time in the course of the cycle. But let's just focus first on this word. So carboxylate, you might recall being this group right here, the conjugate base of a carboxylic acid. And so you can get the idea that if I have some molecule and I cleave this thing off, what I'm going to wind up with when I'm done is R with an H attached to it. Come on over here. And a carbon dioxide molecule that I've now thrown off. So this is going to be a really important reaction to peel this sugar apart into all the CO2 molecules that we're going to make. Now, decarboxylation generally requires a ketone to be near the carboxylic acid for it to happen. How near depends on which mechanism. A garden variety decarboxylation works very well when you have what's referred to as a beta ketone. Now, you might remember back when we did fatty acids and so forth that we called the very last carbon way out here the omega carbon, because that's the last letter of the Greek alphabet. Well, if I've got something built more like this, I refer to this as the alpha carbon to my carboxylic acid. In fact, you've heard that already because it's what we called the central carbon in an amino acid, because it was the one right next to the carboxylic acid. Well, the presence of a beta ketone encourages this to get thrown off. So with a beta ketone, you can get just standard decarboxylation. If I have an alpha ketone, so one where it's sitting right here, and then whatever else is behind it, an alpha ketone generally lends itself to what's called oxidative decarboxylation. So we've already assessed decarboxylation involves me throwing off a CO2. Oxidative, what am I going to remove if I oxidize this in the process? Okay. Hope what you came up with is a pair of H's. And so that's essentially what we're going to do here. The reaction that's necessary to get me from here into the citric acid cycle is going to turn us into something called acetyl CoA. And it involves an alpha ketone mediated oxidative decarboxylation. Say that 5 times fast. So the new player that's going to be involved in this, I'm going to show you it in all of its glory in a moment, and then we're going to boil it down significantly, is called coenzyme A. And coenzyme A actually has some things that might look somewhat familiar. This whole chunk of coenzyme A looks an awful lot like a hunk of DNA. Notice that is a ribose right here with a phosphate at its 3' carbon and a phosphate on the 5'. That is looking an awful lot like adenine, if I'm remembering correctly, but I might have to go check. And then we've got a little bit of extra stuff going on here and a thiol eventually at this end. What we're actually going to do in this oxidative decarboxylation is we're going to attach this mess to our molecule. And in doing so, we're going to remove one of the carbons in the form of CO2. So let's take a look at how that's going to work. That's the thiol right there. That's the only part of coenzyme A's structure that we actually care about. Remember, the way organic molecules usually work is we care about the functional groups. The rest of it, yeah. So, if I have a thiol like this and an alpha keto carboxylic acid, so take a look again, this would be a perfect example of that. It's got a ketone. In fact, it's basically the simplest alpha keto carboxylic acid I can come up with, and a thiol. What we're going to do is remove 2 H's and a carbon dioxide. So, one way that I like to think of this is that the first step of it is essentially to decarboxylate. And if I decarboxylate this thing and just rip off the COO, if I think about what that's going to generate for myself here, let's go back to this example. If I rip this off, what I wind up with as the CO2 flies out is an aldehyde. There's my thiol, and now all I got to do is take those 2 H's, peel them off, and I now have this whole thing attached. Okay, again, with whatever's downstream. In the case of our pyruvate, this is just a CH3 right here, but that gives me this when all is said and done, and then of course whatever was attached to the thiol as well. And so coming back to the PowerPoint, we've made the aldehyde. I oxidize the aldehyde and the thiol, rip those H's off, and that's what we end up with. So our final result of these 2 guys doing their thing and all this stuff, and of course since I'm doing an oxidation, I'm going to need a coenzyme. Final result is that I reduce the coenzyme, I pop off the green circled stuff as CO2, and what I'm left with is the coenzyme and its sulfur attached right there at that carbonyl. And so we call this acetyl, which is the name for this group right here, CoA. All right? So if I'm continuing to work through my worksheets and add things, bear in mind that means that on the reactant side here, I'm going to take for each of these pyruvates, I'm going to be consuming an H+, I'm going to be consuming an NAD+, and a coenzyme A, and then I'm going to be generating NADH and H+, along with a CO2. And in fact, right away, if I want, I can cancel out the H pluses on either side. Those aren't going to really be involved. Now, acetyl CoA I've made really big on your structure here, or on your worksheet rather, because this is an incredibly important molecule. This is also going to be what we turn fats into in order to bring them through this. So any compound that I can break down into the form of acetyl CoA can do everything else that we're about to do in the course of the rest of these videos on the citric acid cycle and oxidative phosphorylation. That's the reason we call it the common catabolic pathway. Once we get to this point is what everything does. Now, we've got one last weirdo reaction, and what that's going to look like is essentially the addition of a methyl group. So here's the methyl group, the CH3. I've shown one of the H's on its own. We're going to add this across the carbonyl. This is not one I'm ever going to ask you to actually reproduce for me. But this is what it comes out to look like when it happens. Essentially, the H goes onto this O, and everything else winds up attached at the carbon, so that I now have this giant species with 6 carbons located in it. This is the production, essentially, of citrate. And the very last thing we're going to do in order to get into the cycle is we're going to hydrolyze off coenzyme A. So remind me, if I'm hydrolyzing, what other reactant am I going to need? Yell it at the screen. Hope you came up with water. That's what we're going to need right here. And as we always do, we're going to add the OH to the carbon, the H to the sulfur, hydrolyze that thioester linkage. And of course, because we are in physiological conditions, the H plus that would be attached on that OH is going to pop off into solution as a weak acid. And we're additionally going to now have the coenzyme A by itself. So be sure to write those in underneath reaction 1, using a water, generating as well an H+ and a coenzyme A. And at that point, if you like, you can cancel out coenzyme A there with coenzyme A from the first little preparatory step of the citric acid cycle. And that's what we've got so far. Now, what we're going to do from this point forward, now that we've got that worked out and we're in the form of simply citrate, of the citrate ion, is that we are going to take a quick pause and then jump full force into the citric acid cycle now that we've got the right starting point. And the way the cycle is going to work is that we're essentially going to do a bunch of things that turn citrate, the molecule that we just made, into the little thing we saw right before that, the substance that is present here with 4 carbons on your worksheet. Let me go back to it for a moment. This guy right here is called oxaloacetate. Okay? Oxaloacetate is a really, really important substance. And as I said, the goal here is going to be that we will take the citrate that we've just made, we've ripped the coenzyme A off of it, we're going to remove 2 more carbons from it and eventually turn it back to this. Because here's the thing, if I can turn it back to this and unload those carbon dioxide molecules, I will have completely chewed up the pyruvate that I started with, and I will have this thing ready to bond the next molecule of this. Then I make this, then I start it all over again. That is the reason that what we have here is a cycle. So step 1 of all this, or steps 1 through something or other of all of this, will be us bit by bit peeling off those carbons, doing the oxidation that I'm describing. Once we've done that, the end game is going to be turning the resulting 4 carbon species back into oxaloacetate so it can wrap around. And I'll see you on the next video for that.